I am now recording. Number one, we just went through on the quiz. If you missed that, I will talk with you about that in a one-to-one, okay? Sorry about that. Let's go on to number two. Any questions about number one?
I'm not condescending you. I'm saying, you know, the best you can do is ask for exactly what I asked for. And, you know, other than that, it's out of your control.
Okay, I tell you what, I'm going to mute. Oh.
Okay.
Okay, so let's go on now. There's a couple of you that don't have your microphone muted. I could hear some conversation going on. So right now, if I'm going to unmute it for a second and see if anybody has any questions on number one. Okay, I'm going to unmute it. Okay, I don't hear anything from anyone. Okay, also I do have chat up. If you've got a question, hey, Thomas, thank you. Whether should be recording, I see it, I didn't have chat on either. Okay, so, all right now, okay, so let's go on to number two. All right, question number two. And when you get to the point, when I finish the discussion, make sure you let me know if you've got questions. Okay, question number two was, there was a limit and there was no denominator. There's no radical on this situation. So all you need to do is plug 0. It says the limit is x goes to 0. So if you just plug in 0 into x then, and get the solution, that is the answer to the question. And most of you did that wonderfully. There's a few of you that left that off and did it another way. There's a couple of you that plugged it into a table and you came close to from above and from below. That's really killing time. It's more on an assessment when you are in a crunch time. I mean, it's a good answer if you check above, coming in from the above and coming in from below. And that does give you the correct answer, but all you have to do is plug 0 into the function. And if you plug it in, you get the answer of 1. And make sure you show the math. There were a couple of you that did your math incorrectly on that situation. One of you did it incorrectly and got 1, but the math wasn't right. So make sure your math is clear on that, right? Questions on number 2? Okay, number 3. Number 3, there were several of you that plugged in -1 into this function and got 0 over 0, okay? In the future, that will mean, it'll mean something. Like I've said before, that L'Hopital's rule is something that will happen when you've got a circumstance like that. But one of the things that, with this problem is I wrote on your quizzes that what you need to do is if you get something that's what's called an indeterminate form or it doesn't work, see if there's a possibility that you can factor it. Can you manipulate the numerator and denominator in such a way that something cancels out? And if that happens, it simplifies down, you might lose the problem that's causing your situation to be indeterminate, to be undefined. You know, you get 0 in the denominator or something. So in that problem, I'm going to go ahead and put it over to my, I'll put it over to the iPad and we'll go from there. I want to share you this. So the general idea is that it is a matter of taking the original function. It's taking a second for it to get, here we go. So if you've got the problem, limit as x goes to -1 of, the reason I'm going through this is because there were several of you that, probably about half of you, that that said you couldn't determine it. But here's the situation, here's the problem, and now it's a matter of recognize, can I factor either of them, both of them, does anything cancel? So it turns out that the numerator, you can cancel. Notice this, we still want the limit. The word limit notation needs to still follow through. We're still checking out the limit. So the limit of this is equal to the limit of this. And there's an x squared common in both terms on top. And that factors out to be x plus 1. So now it's a matter of seeing. X squared doesn't go into the factor into the bottom, but does x plus 1? Yes, it does. And therefore, you're going to get some cancellation. So the denominator, x squared minus 1, is the difference of 2 squareds, is x minus 1 factors into x plus 1. These cancel. So now this is equal to the limit as x goes to -1 of x squared over x minus 1. Now, this is the situation that now you're to a point where, does the -1 cause the denominator to be 0? No. Okay, so now you can plug it in and just get your answer. When you plug in the value for x, LIM goes away. Okay, you're saying the limit as x goes to -1 of this formula. Okay, but if you plug in -1, then you don't need lim anymore. So we're going to plug -1 in, and the lim goes away. So now this is equal to, I'm going to move it down here, -1 squared over -1 minus 1, which is equal to 1 over minus 2. And that is equal to, and there were a couple of you that left your negative sign in the denominator. A mathematical nuance that we've accepted along the way is that either the minus sign goes in front at the halfway bar or above. So this is equal to -1/2 would be the correct notation. If you, there were a couple of you that left the negative in the bottom, I took off 1/100 of a point just to get your attention and say, come on, this is old stuff. Don't leave a negative in the denominator like that, okay? So I took off 100. That shouldn't make a difference in grades or whatever the situation, but just get your attention on that. Now, you know, make sure it's not correct math to leave the negative in the denominator. Okay, so the limit, so this is the answer to the question, -1/2. Any questions on that, on number 3? Feel free to speak up. Okay, I'm gonna go back to verify that we got the chat open. Okay, good. All right, so let's check now. Let's go down to number 4. And if you have questions, make sure you speak up. I've got my mic open. I know I can hear it. I've got you all unmuted. So you should be able to connect with me if you got something you want to say, all right? Make sure you do that. Okay, so number 4 now. Number 4 is a piecewise defined function. And there's 3 questions related to it. One of them is related to limits. The first 2 are related to limits. And the last one is related to continuity, all right? So one of the situations is with limits, we have a situation where if you look at the way it's defined, x is greater than 1 for part of it, and x is less than 1. Notice x is never equal to 1. Okay, that's a real big thing. Continuity-wise, that's a problem because it's not defined at x equals 1. Therefore, the answer to 4C is it's not continuous, okay? You have to lift your pencil. It is not defined at x equals 1. Now, when you talk about a limit, the only point that's missing is at x equals 1. So when you come in from the right, there were a couple of you got those 2 switched around. But if you come in from the right, you notice that x is greater than 1. So I'm going to go back to my iPad real quick here. Okay, so it's coming shortly. But if you've got, it's 3x minus 1 when x is greater than 1. Okay. All right. So when you're coming in from the right, that means x is greater than 1. You've got to use this function. So you come in from the right and see where that's going. Well, all you have to do is plug in 1, but coming in from the right is this x greater than 1. There were a couple of you that switched them. Okay, that might have been an accidental, but there were a couple of you that didn't denote which was which. You just said coming in from the right was 2, coming in from the left was 2, and the answer when you plug in x equals 1 is equal to 2. So they're all the same. Well, I want you to show me part of a correct solution is that coming in from the right corresponds to 3x minus 1. Okay, so the limit as x goes to 1 from the right is this one, because that's x greater than 1. And then the other part, the 2x squared, for x is less than 1, all right? This is for the limit as x goes to 1 from the left, all right? So the less than goes with from the left, the greater than goes with from the right. And when either case, you just plug it into the function and get the answer, and you end up getting 2 in both cases. So you get 3 times 1 minus 1 is 3 minus 1, that equals 2. And if you plug in 1 into the bottom one, you get 2 1 squared, which is 2, okay? So you get 2 in both cases. So yes, as you come in from the right, you're going to 2. As you come in from the left, you're going to 2. Therefore, that's the only point that's missing. Therefore, the limit is at the same place, and therefore the limit is there. It exists. The limit exists, okay? So as long as the limit as x goes to 1 from the right equals the limit as, I should put of g of x, as x goes to 1 from the left of g of x, then that equals the limit as x goes to 1 of g of x. That's it. That's the answer. So in this case, the limit is 2. So the limit is defined there. The continuous function is not. Several of you, I think, because the limit was there, you felt like the hole was filled. But if you look back at that rule again, there is nothing set up for g of x for when x is equal to 1. What we did up there when we came in from the right and from the left, we just said the limit existed. But the function is still not defined there, okay? So make sure you get that squared away. I'll probably ask something similar to that on the test tomorrow. So make sure you're confident. Now, any questions about any part of that, A, B, or C? Make sure you unmute your mic, because right now I can't hear you. Okay.
I do have a question about resubmitting the quiz if we
Okay.
add corrections.
Okay,
Where do we
go ahead.
submit it?
Go ahead, Courtney. What is it?
Where do we submit it once we've applied the corrections?
Yes. Once you've made the corrections and you want to turn it back in?
Yeah.
Okay. Well, it is a matter then of, I would like you to attach it and what, email it to me? I guess that's what, is that what we can we do that? Yeah, I think that's going to be the most convenient way to do it, because it's not going to be accessible via the original problem set in As You Learn. So I would ask you to, if you could save it again and send it as attachment, make sure you include the original and your corrected answer, okay? If it can be on one sheet, that'll be easiest, less, you don't have to do two pages or anything like that. That'll be great, all right? And gradually we'll get that, and even if we don't get that immediately, we'll get that downstream. But the goal would be to get that down, a good part of the review for the test tomorrow. Rewrite it, get it right, get it in your brain that your hand wrote it. And as a result, the muscle memory will take you there when you're doing the problem, so to speak. Okay, any other questions at all about quiz 1? Hey, thanks for asking that, Courtney. That probably answered questions for a lot of people. Thank you. Okay, so anybody else have any questions on the quiz?
Yeah, in the chat there is.
Are you solid? Oh, okay. Matthew, plugged in the equation in Desmos to check at -1. Okay, so remember the situation. The last problem. Are you talking about number 3? Okay, you plugged in -1. Okay, if you plug negative, the question was asked about, we plugged into the equation into Desmos to check, and at -1 it was undefined. The original function is, yes. And therefore, the situation is, notice the x plus 1 when I did the problem, the x plus 1 is what canceled. And that was what caused the denominator to be equal to 0. So back in the original function, that x plus 1 is still in there. So there is going to be a hole there. Okay, so it is undefined there. That is correct at -1. So it is undefined there, but notice that that means there's a hole, but as you come in from the right and if you come in from the left, it's going to be going into that hole. So it will be defined in that -1/2, turns out to be the result that comes from that, okay? So good question. Thank you for asking, Matthew. Does that answer it? Okay, yeah, I see you got it. Okay, great, thank you. Everybody else, I hope you heard that too. Any other questions at all? Hey, thank you for pointing out, Thomas, that I have the chat on now, so I'm looking for that. If you've got questions, make sure you speak up on that line, okay? All right, so listen, I'm gonna want to move to, let's move into some reviewing a little bit. I want to go through some things that we didn't necessarily talk about explicitly. I did mention it in one of the videos, but I do want to go over it again from section 1.5, and that has to do with as x goes to infinity type scenario. Okay, so I have put back up on screen 1.1.1 through 1.5 if you can still be working on those until tomorrow, until the end of class tomorrow, till 1. But I want to look at one of the things that I got up on the screen here in another setup is section 1.5 in Sapling, in the text. So I want to go through some of the things that it says in the text, and you can go back and look at this yourself. But section 1.1, no, I'm going to 1.5. Let's go to 1.5. Okay, here, example. Yeah, as you're coming in from the left and coming in from the right is the key point I want to get to. So investigating the limit as you come in from the right and you come in from the left of 1 over x. All right, in this case, the example 1, notice you can look at your graph and get the solution. Yes, you can write it in the table and get the answer. As you come into 0 from the right, that means the x is positive. 5, 4, 3, 2, 1, 0.5, 0.1, 0.1 over 0.01. They're all positive. And therefore, this is coming above the x-axis down here. Whereas if you're coming in from the left, everything's going to be negative. So it's going to be down here. The same exact graph, but in the negative side of the situation. Okay? So that's an important thing to remember, that when you're coming in from the right or from the left, positive, negative makes a difference. And remember the first part of the question, it was x squared, 1 over x squared, which meant that it was always squared. That means the answer is always positive. And they're both going to positive infinity. You know, one other thing I want to mention is sometimes a little bit later on, in particular in Calc 2, notice that both of these, from the right and from the left, they're both going to positive infinity. So sometimes while the answer is going to infinity, you might say it does not exist, but one other possible answer is positive infinity, because they're both going there. Whereas in the second part down here, one is going, as x approaches 0 from the right, you're going to positive infinity. And as x goes to 0 from the left, you're going to negative infinity. This one absolutely does not exist. They're going to 2 different places, okay? So sometimes notation, it'll be important to be able to recognize if they're both going to negative infinity, then you might say that it is negative infinity is the answer, okay? Does not exist because it's going to infinity is also probably an acceptable way to approach things. But downstream, if they're both going to positive infinity, then positive infinity could be a better answer, a more explicit, a clearer answer than just saying it does not exist, okay? So we can talk about that another time. But for right now, I want to move on to look at a couple of examples here. This is kind of an important one because this is something that could possibly come across on a quiz. Look at this first question. The limit as x approaches 3 from the right, okay? Okay, so in this situation, what they talk through here is that as you're getting close to 3 from the right, as you're getting close to 3 from the right or from the left, this is getting close to 3 on top. The numerator's going to 3 times 2 plus 1, that's 6 plus 1, that's 7, that's positive. So the numerator is definitely positive. But as you're getting close to 3 from the right here, you're at 5, 4, 3, 3.5, 3.1. All of these values are greater than 3. So therefore, when you subtract 3, this is always going to be positive. all right? And as a result, you've got positive over positive. Therefore, as you're getting close in the bottom, this is getting closer and closer and closer to 0 in the bottom, which means this thing's going to infinity. You got a constant over going to 0, all right? And that means, so it's going to infinity. But since it's positive always on the bottom and top, that means it's going to positive infinity down here. The indication is here. Whereas if it was coming from the left, when you get close to 3, this is still positive 7, but this is less than 3. And as a result, you get negative. That means it would be going to negative infinity. This problem specifically was saying from the right, so the answer is positive infinity, okay? And that's a key thing I want to point out. Be conscious of that. From the right, from the left matters in those kind of situations. Okay, so let me go on down. I want to talk about any other questions you want to ask about that? Remember to unmute your mic if you ask something. Okay, so, okay, Cassie. No, the question about chapter 1 homework, no. I put that up there in case you didn't get a chance to go through it. I didn't want to lock you out and so you couldn't see the problem, so you can go in and do it. No, do not turn it in. You don't have to turn in the homework for chapter 1. It's all, you've got full credit for it. Okay, so now what I want to do is I wanted to go through back to section 1.5. All right, so I'm going to go to the share screen moment and go back to, okay, so chapter 1.5. Oh, it looks like you might not be seeing the screen. Can you see the screen, the book text right now? Could somebody give me a yellow thumbs up if you're seeing the screen? Okay, good, good, good. All right, so let's go back here to the screen now. And all right, now, what I want to do is, so I'm going to make sure we're sharing screen. Yes. Okay, now what I want to do is go down here to a couple other problems.
It's not showing now.
Okay, good. Thank you. Thank you, thank you, thank you. Okay, so now?
Yeah, you're good.
Okay, good. All right, so notice these rules, you guys. Limits, limit of a sum. If you've got the sum of two functions, that's equal to the sum of the limits. You can split limit onto each one. Product, same exact thing. Quotient, same exact thing, as long as the denominator is not equal to 0. So the limit of a quotient is the quotient of the limits, as long as the denominator is not equal to 0. The limit of a power is equal to the limit, the limit of a power, f to a power, is equal to the power of the limit, okay? And the limit of a root is equal to the root of the limit. So it follows through all the way the situation, and that'll carry with us in a variety of different things throughout calculus. But this is a key part of this situation. Also, is what I want to do is recognize this, that if you're coming in, look at these examples, example 5. As x goes to positive infinity, the denominator's getting huge. 5 is a constant. Doesn't matter if it's 5, doesn't matter if it's 1,000,000. As you go to infinity, 1,000,000 becomes nothing, okay? So the denominator's getting huge, this is going to 0. If you've got a root, it's not going as fast to infinity because the graph slows down, but it's still going up. So even if it's a root, it's still going, the denominator's getting huge, that's going to 0. Even if this was 1,000,000 over a square root, it's going to 0. One of the other things I wanted to point out, though, that they didn't do here, yeah, and this one, as x goes to infinity, no, we're all set. Okay, let's go down to part C. As x goes to negative infinity now, okay, if it's negative on top or if it's positive on top, doesn't matter. In the end, the graph is going to 0 because this is like this. This is getting huge. As x goes to infinity, whether it's positive or negative, it's causing the denominator to get bigger. And if the whole thing's positive, then it's going up to, then it's, as you're going to the left on the X, it's still approaching the X-axis. It's approaching Y equals 0. Either way, whether it's from above or from below. As you go to negative infinity, same situation here. We've got a radical that on the bottom, that's going to 0. If we've got an exponent's bigger than 1 on this one, this is going to 0 also. The denominator is, X is in the denominator, the problem's going to 0, okay? Any other questions about that? Okay, kind of quickly here, let's look at this. They go through the examples on example 6. As X goes to infinity, water of T it is. Okay, so as X goes to infinity on A, notice what's happening here. We've got a constant. As X goes to infinity, that's not touching this. It's going to 2. But as X goes to infinity, this fraction right here is going to 0. So as a result, you end up with the limit of this is equal to the limit of 2, which is 2, and this is the limit of 3 over X, which is 0. The answer is 2. Now in this situation, again, anywhere the X is in the denominator, it's going to be 0. So this is 2 plus 0. This is going to infinity now. It's not, if this is going to 2 or 3 or negative 1, that's a different creature. This is going to infinity. That's really important, okay? If it's going to infinity, then this fraction right here is going to 0. This is going to 0. So you end up with, right down here, so the limit of this product and the sums is equal to the sum of these limits multiplied together. And you end up with 2 plus 0, boom, and 1/2 minus 0, boom. So you get 2 times 1/3, which is 2/3, okay? This last one, they go through the trouble here of something that I'm going to talk with you in just a second, a little differently. But the idea here is that you're given this 1/4 in front of this. Remember, they go through the trouble of splitting up this X squared under here, and under here. But what's the lead term? When we get down here, the next example, we're going to be talking about all you got to worry about is the lead term. As X goes to infinity, these other ones are going away. The math of this is right. When you get into Calc 2, you're going to need to use this method, to split that denominator under each numerator, each 3 separate fractions like this, like this down here. And you see that you get 3 plus 0 plus minus 0, okay? But they don't go into that explicitly here, but this is what's happening. So you get the limit of each of these terms. This is going to 3, this is going to 0, and this is going to 0. So you end up with 3. That's right here. And 3 times 1/4 is 3/4. I kind of went through that in a heavy way. Has anybody got any questions on that?
Yeah, I got a question.
Go ahead.
So part of the process, it's always just safe to assume to simplify the function is to its most basic form.
Yeah. So look, well, I'm going to answer that in the next couple questions, okay? We're packing stuff in here. They go through the process in the book several different places. They introduce one thing, they go a little step further, and then they change it a little. And then they change it a little. And then you get to the end result where you could have done that from the very beginning also, okay? We're moving through this fast enough that I'm not going to require you to go through all the different steps of the way. So if you ever in the future have to split this up and use that procedure, there's times when you'll need to do that. You'll need to do that to simplify and get that. But for right now, all you need to do, you don't need to go through the process and split this limit onto each term, Going to the answer will be totally sufficient. Show me what you did. Like they did this a little briefly. If you did this part, then saying that this is 3 plus 0 minus 0, like they did up here, that I think they did that for one problem. Whatever. But they were like right here, they showed this is 2 plus 0 equals 2. That shows you understand it. you did this right. If you went from here to here, that's wonderful. You said this is 2 plus 0 times 1/3 minus 0. That going from here to here would be wonderful, okay? So you don't need to show every intermediate step, if that's what your question was, okay? Is that what the question was?
Yeah, I got you.
Okay, good, good, good. Now look down here. See, they go through the process in example 7. Watch this with me. I think this is good for the sake of the math. They go through the process of how do you algebraically get what the solution of this is? Well, mathematically, if you find the largest power of all these exponents and you multiply the denominator, you multiply, get the that underneath every term, that's what they do here. That's what they do in the process of doing this problem. The largest exponent is 3. So they got x to the 3rd under each term. They multiplied the top by 1 over x to the 3rd, and they multiplied the bottom by 1 over x to the 3rd. And then they split it up, yada, 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 got that situation, etc. But you can look right now and get the answer to this. Because one of the rules that we're talking about when you have rational functions is you're only worried about the lead term. So you look at the lead term of the top and look at the lead term of the bottom. So the answer to this question, if you follow through and divide through by x cubed all 4 terms, you get this, okay? You get x to the, when you put x to the 3rd under x to the 3 halves, well, that's 1.5. That means you got x to the 1.5 on the bottom, right here, left over. X to the 3, this is 6 halves, this is 1/2, so you end up with 5 halves left over in the bottom. This again, x to the 3rd under x to the 3rd gives you 1. But x to the 3rd under 2/3, 2/3, this is what, 9/3? That gives you 7/3 left over on the bottom, okay? So if you go through that whole process, then this is the limit of each of these terms. This is 0, 0, 1 minus 0. That's what they have here. But what we're going to be talking about shortly is you can look right now, right here, and you know the denominator, the exponent there is bigger. So this rational function, as x goes to infinity, is going to just this lead term is all you need. And that's going to 3 over, x to the 3 halves. And as x is going to infinity, no matter what's on top, you got x at the bottom. This is going to 0. So the trouble, it takes you quickly to where this answer takes you. If you want to do this math, it's time consuming. And in the future, you're going to need to understand how to do it. But to answer this question, what's the limit as x goes to infinity? You got the answer right here. You look at this, you can tell me that right now. This is going to 3 over x to the 3 halves. Well, you don't even have to say that. This lead term is the denominator is going to be larger. It's going to be left over downstairs. Therefore, this is going to 0, period, right now. Okay, any questions about that? Okay, look at this next one. This one is even more cumbersome because it's got a radical, okay? Right now, on the test tomorrow, all you got to do is look at the lead term, okay? And what's the square root of 4x squared? Square root of 4 is 2. Square root of x squared is x. What's 2x over x? 2. Got the answer right there, okay? That's all you need to do if you have a problem like this tomorrow. It's going to infinity now. That's important. That's critical. But if you've got something like this, look at the math they had to do to show the math of why it works, on both of these. It's messy. There's opportunity for mistakes all over the place. Don't have to do that. All you got to do is when it's a rational function, you look at the lead term of the top numerator and look at the lead term at the bottom, simplify it. That's 2x over x. That factors down to 2. The limit as x goes to infinity of 2 is 2. Okay? Questions on that? And you can do that. I'm sorry, I didn't give you time to answer, but you can graph it. I really want to say on this test, you guys, use all your weapons, okay? Don't use somebody else, okay? This is a really trustworthy moment, you guys. I'm telling you, you can use your calculator, you can use all the tools. I'm giving you 3 hours on this thing. So you've got time to do it, all right? Stop, look at the graph on your calculator, put it on Desmo, see if you get it. Make sure it makes sense, okay? And graph this thing. This function looks like this. And as x goes to positive infinity, you're going out here, and that's approaching 2, okay? Look up here, this first one. Do they graph that one? No, they don't graph it. That's okay, but graph it and verify what the situation is, okay? Now, real quickly, I want to do through 2 more examples. All of these on example 8 are pretty straightforward, I think, all right? So all of these are just polynomials. They're all upstairs. There's no denominator. As x goes to infinity, you look at the lead term. Look what they say here. You look at the lead term, that's all you got to do. That's going to infinity. The answer is going to infinity. As x goes to infinity, look at the lead term. Boom, infinity. Negative infinity, okay, now this is important, okay? If you look at that lead term, this is to the 4th power. If you had an x to the 3rd, x to the 2nd, and all this other stuff here, all you're looking at is the lead term. As x is going to negative infinity, the even exponent cancels out the negatives, and you end up with a positive value. So the answer to this one, as x goes to negative infinity, is positive infinity. Okay, and this one, if it's got an odd lead term, odd exponent, for the leading term, then you've got on x, then as x goes to negative infinity, this is negative. So you get negative. Any questions on that at all? Okay, now let's go to number 9. Okay, here's what it's saying. You got a polynomial on top, you got a rational function. Polynomial on the top, polynomial on the bottom. The limit is determined by the first term, period. You can disregard everything, no matter how big the other numbers are. As you go to infinity, it comes down to what the lead term is. So that's it. That's the whole situation. So look in here. And here are 3 different, they give 3 examples here. I really want you to see this. All right. So we've got the lead term. Notice you've got to have it in descending order. The lead term needs to be recognized. I could possibly mix these around. And the lead term, if the minus 2x was in front, then the lead term wouldn't be. The lead term of when it's put in correct descending order, we need the exponent to be the positive 2 over the positive 2. Now, when this happens, the answer is the limit as x goes to infinity of this. The x squareds cancel, you're left with 3. That's the answer, okay? So you're left with the graph here. You can see it crosses, but as you get closer and closer to positive infinity, it's going back up to 3. Look at this situation. We've got in this situation, you go to the lead terms, you get the numerator is x squared, the denominator is x to the 3rd, bigger on the bottom. You just look at the first terms. If you you cancel, you end up with 4 over x. Doesn't matter what's on top. X is on the bottom, this thing's going to 0. So even if that was 1,000,000 x squared over x to the 3rd, and you could have 0.1 x to the 3rd, okay? Doesn't matter. This x to the 3rd wins, because when you factor the thing out, you've got x on the bottom, and as that goes to infinity, no matter what's up here, it's insignificant compared to where x is going. So the answer to this one, remember, there's an x left in the bottom, so that means it's going to 0. As x goes to infinity, it's going to 0. All you got to do is look at the first term and tell me that, okay? No matter how complicated it is. And this last one, notice what this is. X to the 2nd is left over when you cancel these on top. X to the 4th over, they've got a coefficient, so you got 5x to the 4th over 2x squared. You cancel out, the x squareds are gone, you got 5x squared over 2. The 5 and the 2 make no difference. you got x squared on top. This thing's going to infinity. As x goes to infinity, it's going to infinity. Just like this is showing down here. Okay? So you end up with x squared, which means in the long run, it's going up to the right and up to the left. Okay? Questions on those examples? Okay, so let's see here. That's what I wanted to hit. Okay, I want to touch a couple things on 2.1 real quickly, okay? I'm gonna go back to section, I'm gonna go ahead to section 2.1 here. I want to get you back on the screen though. So I'm gonna share a screen, go back here. Okay, so we're here. I'm gonna go back to section 2.1. Chapter 2, section 2.1. Okay, one of the things I want to hit here is remember the terminology of what we're talking about. Let me hit 2.1. Okay, so remember when you're talking about rate of change is the slope. The slope of the tangent line is the rate of change, okay? The slope is talking about the rate of change of the graph. That's what we're talking about, rate of change of a function. What is the slope? Change in y over change in x. Now, when you talk about instantaneous rate of change, that's saying you're getting one specific point. Average rate of change is you got 2 points, okay? And you're getting an average between those 2 points. What's the slope? But when you're saying instantaneous, you're finding at 1 point. And that's using the limit definition, okay? And if I ask you to do this kind of problem on the test, remember the situation here. Let's look at this example. They've got, I'll give you the formulas, okay? And remind you that this is the limit at a point. If it's instantaneous rate of change at C, then you can use this formula. The limit as x approaches C, f of x minus f of C over x minus C. So let's look at this example. I was going to work through one, but they do this here in the text. So it says, find the rate of change of the function at C equals 2. So what you do is you go down, you go plug in the function. The rate of change of f is that you use this function right here. It's the limit as x approaches 2, boom, f of x minus where the point is, f of 2, over x minus c, which is 2. So you just plug in 2 for all the c's here, okay? And the idea then is you plug the limit stays until you plug in the 2, all right? So the limit, so you plug in the original function here, f of x is that. And then you subtract, you got to do the calculation of what's f of 2. Well, they show it here. F of 2 is, plug 2 in here, you get 4 minus 10. That's 4 minus 10, you get negative 6. So you get f of x minus negative 6 over x minus 2. And every time you do this, you guys, the numerator is going to factor, and it's going to cancel with one of the factors in the denominator. And in this case, the denominator is x minus 2. Therefore, x minus 2 is going to show up here. This is the first thing you do. If it's messy, and you got a coefficient that's got a multiple in front. If you've got x minus 2 on the bottom, there's going to be an x minus 2 on top as one of the factors. Plug that in, it'll save you time factoring. So x minus 2 is on the bottom. Notice this factors into x minus 2 minus 3. You get plus 6, so they both got to be negative. 2 and 3 gives you 5. Okay? And then as x goes to 2 now, these cancel. So now you can plug in what's 2. So when these cancel, the limit becomes this. Notice you needed the limit, all the limit notation, all the way through until you plug 2 in. Plug 2 in, limit notation goes away. So you end up with 2 minus 3 would be the next thing. That's minus 1. Okay? Any questions on that? Because there's a good possibility I'm going to include that on the test tomorrow, okay? A question like this. Now, I want to, so that is that. I wanted to make sure you saw that. Okay, and then remember this, you guys. I'm going to ask you to go through to section 2.2. And that is this. I'm going to go to section 2.2. So we'll go back here to the table of contents, chapter 2, section 2, 2.2. Okay, section 2.2. All right, now we've got the derivative of the function. The derivative of the function now has been set to be this now. We're changing it. I had said it in one of my videos, one of the recordings, that changing it to the limit as h goes to 0. That original function was the limit as h goes to x goes to c. X goes to c was what we had. We changed that to become as h goes to 0. We added h, we made the difference between these two spaces of h. X plus c plus h and c. The difference there is h. So c plus h and c, that makes it the limit as h goes to 0. In the long and short of it, what I'm trying to say is now the derivative definition is the limit is h goes to 0, and all you have on the bottom is h. Before we had x minus c, and now that this notation is there, it's just going to be h. Now, if you use this, you've got to carry the limit notation. There's a problem right now. H is in the denominator. As h goes to 0, we got a problem. So in all the problems, remember, you could factor an h out of up on top. And when you factor that h out, these cancel, and therefore now h can go to 0. So you can't plug in, this sign needs to be here, this limit notation needs to be here until this h goes away, okay? So for instance, let's look at this problem. They've got one that's a little more complicated. I want to do one that's a little simpler. Let's go to section 2.2. There's one in 2.2 that I want to look at. Okay, so, no, they did pick that, didn't they? Okay, let me hit the one that I want to show you guys. I'll tell you what, let's do the one that they did. They did 2x minus, x squared minus 5x. I'm going to do that on my iPad, okay? Let's do that on my iPad. Let's go to there now. I want to go to my iPad. Okay, so I'm going to go to new screen. Okay, so what I want you to see is if I said if f of x is equal to x squared, what they said in the text, what was that? X squared minus 5x, I think? I think they did. X squared minus 5x. All right, so the situation is that the idea is that f prime now, I'm going to give you the definition here, but it is now equal to the limit as h goes to 0 of f of x plus h minus f of x. You guys do this with me now, if you would, okay? Do it. I'm going to ask you to do something very similar on the test tomorrow. Make sure you do this. All right, so what do you do first? We plug in f of x plus h. That means everywhere. So I'm going to convert, like I said, I'm going to resort to smiley face instead of lim. I use lim to define what that's there. Make sure you do that. Don't start with a smiley face. Show me what you're smiley facing about, okay? But the idea is now plug in x plus h wherever there's an x. So in the function, we've got something squared minus 5 something. That's f of x. That's f of x. But now I got to plug in f of x plus h. I plug in x plus h. All right? Minus f of x, parentheses. Remember this. There were 2 of you on the quiz, or that left off the parentheses and that messed your answer up. So you've got minus f of x, which is the whole thing goes in there just like it is. All right? And that's over h. Don't just get lazy and say, just do the top, okay? Make sure you include the minus over h. And this is out here until that h disappears. The h is going to cancel in just a little bit. So we end up with the limit as h goes to 0 of x squared plus 2xh. Remember, there's a middle term, plus h squared minus 5x minus 5h minus x squared plus 5x over h. Now the cancellations happen. Plus 5x minus 5x minus x squared plus x squared. Every time, you guys, this whole thing should go away. It should cancel with something, okay? So if it doesn't, something's amiss, okay? And we don't want to be amiss. You know what I'm saying? Okay, but here we go. So now we've got 2xh plus h squared minus 5h over h. Make sure you got everything. There's 3 terms. They all have an h in it. So now I'm going to go ahead and switch back to, don't worry about it if you don't do it exactly the right time. I'm going to factor out an h. Notice that if I multiplied that back out, I get what I started. Check that yourself, okay? Sometimes when we factor, we make little sillies, okay? And just check to make sure you got it. That's what we got for the denominator. Now the h's cancel. Therefore, and I'm going to skip I'm just going to go on to the last step here and say, I'm going to plug in 0 for h here. So the limit as h goes to 0 of this is equal to 2x plus 0 minus 5, which is 2x minus 5. Okay, and notice shortcut mode up here. What I said before, bring that 2 down, that's 2x. Derivative is 2x to the first minus, what's the slope of minus 5x? Minus 5, boom. So the final answer is this. I'll be asking you to do a similar problem tomorrow on the exam, okay? So make sure you're confident with that. Okay, one other thing came up. Any other questions at all? Okay, one other thing I wanted to talk about. I want to go back now to section 2.2. Just about ready to call it a day, okay? And you can look at the recording in a little while if you want to look back over that. But right now, what I want to do is I want to go back to the book. I'm hoping you can see the text right there. Okay, I want to go to 2.2, and I want to look at some terminology that came out when we were talking about this situation, something like this. This grasp, on my recording, this is called a cusp, okay? And the terminology they use in I used the term that they had used on the slides, and they had called it a vertical asymptote, okay? A vertical asymptote in this situation, something like this, okay? Sometimes the word asymptote is taken literally to mean that it can't be that value. Notice that there is a value at x equals 2. There's a cusp there. Notice the terminology they're using here. The graph has a vertical tangent line instead of vertical asymptote. Asymptote being a dashed line, you don't have a value there. Sometimes that can be confusing when you're talking about this kind of a situation. So vertical tangent line can be a little more clear that for both cases, the slope is going to infinity here, all right? And in this situation here, there's another situation, where was that? I wanted you to see this. Oh, it was the cubed root of x. Oh, yeah. The cubed root of x. Oh, I wanted to do that onto Desmos. But the idea is this. Remember that when you're in a situation where you're wanting to say, are each of these continuous? Are each of these continuous at x equals 1, at the point that they're showing here, okay? Is it continuous here? No. This is not continuous. You got to lift your pencil. Is this one continuous here? Yes, you don't have to lift your pencil, okay? So is it continuous here? You don't have to lift your pencil. Here, not here. Does the, yes. So the other question would be, But down, what we're going to be getting into, is it differentiable? And that's going to be a different question that we'll be addressing in another sense there. And that comes out in section 2.2 also. The slope has to be the same here and here for it to be differentiable at this point. So is this differentiable at x equals 0? No, it's not even continuous, okay? So that's not differentiable. This is continuous. You don't have to lift your pencil, but is it differentiable? The slope when you come down here is one value, the slope here is another. If there's any kind of a corner, it is not differentiable at that point, okay? And then you come down to this one. This is, if this was y, it looks like this is y equals x squared, and at 1, that is equal to 1. The slope, but the slope might not be the same. The slope has to be exactly the same here. So let me tell you this. Let's go down to section 2.3. I want to show you this. So where the function has no derivative, here's an example. Here's an example. The slope has to be the same for both lines in order to have a derivative there. This has a slope of +1. This has a slope of -1. Therefore, this has a corner at 0, 0. This is not differentiable, okay? That is an important point. Now look at this one. This is what we had talked about. I had said on one of the homework problems. I said on the recording. This one and this one, notice the slope is going, this is continuous. Both of these are continuous, okay? This one doesn't even have a corner. But at this point, the slope is infinity, all right? So it has a vertical tangent line at x equals 0. That means the derivative does not exist. It's not differentiable if it's got a vertical tangent line. The slope being infinity means it's vertical. If it's going up and the slope has to be infinity, then that means it's not differentiable there, okay? So if there's a corner, and this one here, you could call that a corner, but it's going to infinity. The cusp, it's got infinity going from both sides. So this is not differentiable. This is not differentiable. This is not differentiable. Those three situations. If I ask you about any of those are the three things you got to be concerned about. So not having a derivative, if you notice that this piecewise defined function, tell you what, that's, if you look at the leading term in this situation, no, the situation is that if you have to determine whether the slope at the derivative at 1 exists. And you can see here at the graph, if you plug 1 into here, you get 2. You get -2 plus 4 is 2. And you get, plug in 1 here, you get 2. So it's continuous. There is a point there, okay? But this is upside down. See that? This is right side up. And at that point, you've got a different, there's a corner there. There's something, it's not a smooth curve. The slope here and the slope here is not the same. So this is not differentiable. If you had that type of situation, that would be the solution to that. All right? So, okay, I'm going to stop now and let you ask questions. Does anybody else have any questions about any part of anything preparation for the test tomorrow? Any sapling problems?
So it's non-differentiable if there's any kind of sharp turn at all?
Yes. The start time, I had sent something out fairly recently, I think I did, but the start time is going to be that usual class time. It's going to be 10:20, and I'll have you 3 hours. So 10:20 to 1:20 is the time of the exam tomorrow. So you can come in any time there and do it, but you come in as early as you can, and the end time will be at 1:20.
Is there any content past 2.2?
Any content past 2.2?
2 on the exam?
No, there is not. No, I'm stopping at 2.2.
Okay.
That's going to be the start, and that's going to be included in exam 2. The rest of 2 in chapter 3 is going to be exam 2. Good, that's a good question. Thank you, both of them. Anybody else?
There was a sapling problem in 1.3. It was the first question that confused me.
Section 1.3?
Yeah.
Okay, good. I've got sapling up here, section 1.3 homework. You're saying the first question,
Yeah, just the first question.
okay?
Some of them,
Can you
it
see
was-
this on the screen right now?
yeah.
Okay, great. Okay, let's look at number 1. Okay, so what are you thinking? Is it this graph that you had also is very similar?
Yes, yeah.
Okay, so we got situations here of, on any of these, are there any points here where f is continuous? It looks like there's not a dot here. That's not an open circle, is it?
No.
Okay, so it looks like everywhere else, wherever there's a change, a connection, there's a hole. You got to lift your pencil. But right here, you don't. So there's one place where it's continuous. That's right there. Okay?
Yeah.
So was there any other thing, part of it you wanted to ask about? Go ahead with your specific question first.
Yeah, I was confused. It talks about whether or not one of them is, I forget what it says, but
Okay,
like
let's look at them. Discontinuous.
A re-
Discontinuous.
the
Go ahead.
removable discontinuity.
Okay, good. Removable discontinuity. If you replaced where there's a hole or where there's not continuous with a point, would it be continuous? So here we've got situations. This is continuous, not a problem. This is not continuous. If we filled that hole, would that function be continuous at x equals -2? Yes. Yes, it wouldn't be differentiable, but we wouldn't have to lift our pencil if that hole was empty. That is a removable discontinuity. Look at this one at -1, it looks like. This is not continuous here. If we replace that hole with a dot, would we have to lift our pencil? Yes, you still would. That is not a removable discontinuity. And if you look at both of these, if you fill the hole, it's continuous. So both
Right,
of these,
okay.
okay, that's the whole idea. If you fill the hole, if you made it so that it was, if you made it so you filled the hole, would it be continuous? This one right
Okay.
here is the only one that is not a removable discontinuity.
Okay.
Okay? Anybody else? I can access all the questions in the sapling right now. If you've got anything there, 2.1, 2.2, or chapter 1 stuff. I'm going to go ahead and wait on here just a little bit, just in case you have questions. But the recording, it's going to take a long. This has been on for over an hour. So the recording, it takes a long time for the YouTube to process it. So pretty soon, if you don't ask questions, I'm going to drop off and go to office hours, okay? So we can end this recording and I can start getting it translated into a YouTube. It takes a little while. The longer it is, the longer it takes. So I'm going to, in just about a couple minutes here, if you don't have questions right now, I'm going to go ahead and drop off and switch to the Zoom, the office hour Zoom up at the top of the As You Learn, okay? Anybody else have any other questions about anything?
I have a question.
Good.
So one of on my sapling homework problems, it won't let me submit, like when you click the check answers button, it won't let me do that. It comes up with like a little thing that says you need to reload your page.
Is it
And
chapter 1?
no, it was chapter 2.1, question 3
Oh,
was not letting me submit that question, and the I contacted the sapling support center, and they haven't gotten back to me. Should I?
oh, you did. Well, thank you for making that effort. But 2.1, the third question.
That happened to me too, yeah.
That
Yeah.
happened to me as well.
Okay, let me go. I'm going to go to the third question, and let's just see. Make sure are you confident with with your answer?
I had the same problem, and I believe I have the correct answer. I contacted Sapling, and they actually said that I could email them the answer, and they could put it in for me, but they haven't done it yet.
Well, that's special. Okay, well, do you feel confident with it though?
I believe so. I know I do, I think.
Okay, so the whole thing is we haven't done a lot of practice with normal line. So downstream through the semester, you should probably have that. But for the test tomorrow, I probably won't ask you to do what's the perpendicular line, okay? But if you're asked for that, remember the perpendicular slope is just the negative reciprocal of the original slope that you're working with. So negative 12 became positive 1/12. And then you use the same point, plug it in and see where it takes you. So good. And then graph it on your calculator. Make sure, if you're asked for the tangent line, make sure that the graph touches at that point. Make sure you are comfortable with that. Thanks for mentioning it. I'm really sorry. And thank you for making the effort on it. And that's part of the reason why I'm saying you only got to get 70% to get full credit. And so let me know if you end up falling short of getting enough for 70%, okay? Well, that could be an issue. Okay, so thank you for asking. Anybody else have anything else? Did that answer the question? You really didn't have a question. You let me know. And thank you for following through and contacting them. That was a good move. Because it's not always the rapid response. So go from there. Anybody else have anything? Okay, in about another minute, if nobody comes on or asks, I'll go ahead and switch over and start letting this recording transfer. Hey, thank you all for coming out.